Hello everyone, and welcome back to Neural Networks from Scratch in C++. In this video, I want to explain how we separate the bias from the matrix multiplication. So if you remember from the first video, we were talking about this particular equation. So f of c equals 9 over 5 c plus 32. And we were talking about how to convert this equation, which converts Celsius to Fahrenheit, into a neural network. And the way that we did it was we created a node C, and we created a node F, and we assigned this directed edge from C to F the value 9 over 5. And then we were talking about how, okay, well, we did that for this 9 over 5 because it's multiplying this c, but what is 32 multiplying? So what we did was we created an artificial neuron, and we just put it the constant 1, and then we assigned this edge 32, and we said that this 9 over 5, given that it's multiplying real data, is a weight, and we said that this, given that it's multiplying this artificial data, is called a bias. Well, another way that we could write this is as a dot product, which this should all be review. So 9 over 5 and 32, these are our parameters. If we dot this with c and 1, well, we get f, or our degrees in Fahrenheit. Well, what I wanted to talk about in this video is how this is typically not done this way. So this was a great way for us to draw this as a neural network diagram, but typically what we do is we don't modify the input and create this artificial one. So this could be, well, because we have some particular data structure that we don't want to allocate more memory just to assign this value 1. But the more important reason for why we don't want to do it this way is because we like to separate our weights and biases. The biases you can think of as, well, it's your, these are like completely independent parameters from your weights. So your weights are multiplying real data, whereas your biases, they don't care what data comes into the network. That's why this is your bias, and that's why it's called a bias. You're biased towards some value, assuming you don't have any data coming in your network. So what we really want to do is we want to separate the weights and the biases. So this was a concrete example, this equation, but I'm going to now make an abstract example. So say we have a bunch of parameters that come in to our neural network, and it looks something like this. So we have some vector of some data. I don't know what the data is, but we're going to call it A, B, C, D. And we're going to use the old method of just creating this 1, because the thing multiplying this 1, this is going to be the bias. And now let's say that we have two different vectors in this this matrix. So that's going to represent two different dot products, two different equations. And we're going to specify them as W0, for example, W1, W2, W3, and I'm going to just extend the brackets here. And here I'm going to say B0 for our bias. Okay, and now this W, let's give this another name. I know it's not the best name, but let's just say M for the time being. So M0, M1, M2, M3, and B1. I could have come up with better names, but you can just think of these are a different vector of weights and another bias. So when we do this matrix multiplication, right, so we do this column dotted with this vector, what we're going to get is the following output. So we're going to have all of this dotted with this, and then essentially you're just going to be adding B0 to that result. Okay? So I'm not going to draw it out because that would be a lot of letters to draw, but you can just imagine that. And it's the same thing for the next vector. You can think of it as this vector, this subspace, dotted with this subvector of the input, and then you just add b1 to the result. Well, another way that we could have represented this is as such. Instead of adding this 1 to the first vector, I'm just going to leave it as a, b, c, d, and the parameters, I'm just going to leave the parameters that actually represent weights. M1, M2, and M3. And then what I'm going to do is I am going to separately add a row vector that contains my bias. So let's do that. So this is equal to, well, you can see that this is equivalent to the above. So let's kind of do a bit of a recap. Why did we even do this in the first place? Well, the main reason is because the bias represents something else from the weights. The weights are, they correspond to the value that you're going to multiply by actual data. So they're very influenced by particular patterns in the data, whereas the bias is kind of like what happens if you don't have any actual, if the weights are not contributing in any way. This is kind of what you're left with. So you can think of the bias as, well, this is what your network is biased towards if all of your data is pretty much 0. So we wanted to do that for that reason. The other reason that we don't want to do this is because this is an expensive and unnecessary data transformation that we would have to do on the input just to embed the bias into the same matrix as the weights. So there are a few convincing arguments for why we would want to separate the bias and the weights. So now let's look at how we would do that in code. So what I'm going to do is, well, actually there's one additional topic that I want to discuss. So the additional topic I want to discuss is we looked at this example where our data comes in as this sort of flat row vector. But if we were to have, let's say, a matrix, so let's say 2 row vectors, so let's say A, B, C, D, and once I'm going to add the 1, and E, F, G, H, and then 1, and let's just call this I, J, K, L, B, 0. Just imagine I extend this, and then M, N, O, P, and B1. So our input data, let's say that we had 2 different inputs that were coming in, right? So in this case, that's what this looks like. We have 2 inputs, and they're independent inputs. If we were to do this this matrix multiplication, what you would see is, well, let's think, what is the shape of the output? So we have 2 rows and 2 columns here, so that means we would have a 2 by 2. Okay, so let's do that 2 by 2. So now, if we were to do the first dot product, you would see that you would pretty much get the dot product between this, and then plus b0. So I'm going to call that dot 0, so d0 plus b0. And then, let's say that I move to the next row. Over here, you'd be left with, let's call this d1 plus b0. And let's do the same thing for the next column. So here you would have d2 plus b1 followed by d3 plus b1. And notice if I add another row, so let's say x, y, z, I kind of ran out of, let's say, to be honest, I forgot what this even is. Phi, I don't remember what this one is, but some Greek symbol. Okay, so now I add another one, and you'll see that this is consistent. So now we have a 3 by 2 as our output, and I know I said d0, d1, and I was kind of going down the column, but I mean, I can clean this up. Let's remove this 2 now. You'll see that the pattern is consistent. So now I would have the dot product between this, and I'd be left with, well, in this case, d2 plus b0, and now this is d3, d4, and then I do the same thing for this dot product, and I'm left with d5 plus b1. So I hope you see a pattern here. So you can see that in all cases, all I'm doing is, for the entire first column, I'm adding this bias term, b0 in particular. In this entire column here, I'm adding b1. So now you can see I'm wasting so much space. I'm essentially just going to keep on having all of these b1 when I could essentially do this in a much simpler way. And the simpler way is to use something called a broadcast operation. So I'm going to rewrite this as A, B, C, D, E, F, G, H, X, Y, Z, Greek, for whatever that variable is. And once again, matrix multiplied with I, J, K, L, M, N, O, P. And now I'm going to do something that looks weird. So this is a 2 by 4 by 4 by 2. So I get a 2 by 2 matrix as the output of this. But now what I'm going to be doing is I'm going to add, under a very particular definition of add, B0, B1. So typically, I know we looked at matrix multiplication, not necessarily addition, but the way that you add two matrices is you just add component by component. So for addition, you expect the shapes of your matrices to be identical. So if you have A, B, C, D, plus E, F, G, H, your output is just going to be, well, you look at the first entry of both and you add them up. So now you get a 2 by 2 output of A plus E, C plus G, B plus F, and then D plus H. But in this case, we have a row vector for our bias, which is 1 by 2. So that's why I set under a very particular definition of addition. In this particular definition, what we're going to be doing is we're going to be doing something called a broadcast operation. So I'm just going to circle this so that you don't think that this is a proper matrix addition. But the way that you do this broadcast operation is, well, I'm going to just rewrite the output as these, like in this dot notation. I don't know why I said 2 by 2. This would have been 3 by 4 by 4 by 2. But anyways, let me make an output. So that'll be dot product 0, 1, 2, 3, 4, and 5. So we get 3 by 2. And once again, I'm going to do this weird addition, and I'm going to write B0 and B1. So under this definition, we are broadcasting along the rows. So in the row dimension, we are broadcasting along. So instead of just doing an element-wise addition, you can think of this as doing the following. So what we had before, which I'm just going to put as a big star, so I don't have to rewrite this. But now we can replace this addition with a proper normal matrix addition. And the way that this works is you just duplicate this same value across all the rows that you have. And this is equivalent to if we did the matrix multiplication with all of the original ones in the data. And if we were to kind of fuse the bias onto the matrix. Okay, so hopefully that gives you some intuition for how we're going to separate the bias from the parameters. And in the next video, I want to quickly just code it out. Hope to see you there.